Welcome back, everybody. We are continuing work on our C interpreter today. So last week we left off with support for local variables and assignment. This means that we can now declare variables inside the function, assign them, and then later reference them. And when we execute it, this will print 11 because we've just assigned I to 11. I did two additions of camera. The first is I implemented some infrastructure to get better error messages. So for example, one error we could make is that instead of assigning I, we are assigning ABC, which isn't declared. And another error is that we could declare the same local variable twice in a single scope. And when I run the compiler now, we will see nice new error messages. The Unicode errors, this is part on Neoworm's terminal emulator. It's a bug there, it's not in the output. If we run it in the actual terminal, it will look fine. So we can get like the nice source annotation, and see for a duplicate declaration, we will get both of them. This was pretty straightforward with the way. So I can show you the Lexi already reported diagnostics, and I simply hooked into that same infrastructure to print our diagnostics. The only thing that we needed to do for that is to remember source location for every node in the tree. So I just needed to adjust the parser. I can show you. So whenever we, for example, pass, what's a good example? For example, when we pass a declaration statement, we will pass its position, and then we get the position, and then we insert that position into a hash table, and then we can access the location of every node and use them in the error messages. The second feature I did of Grammar is I implemented compound assignment operators. So like plus equals and not equals, minus equals and the other ones. The implementation was relatively straightforward. So in a way, the compiler just needed to, we were passing an assignment. Previously, we only passed equals, and now we are passing all those other operators. And then in CodeGen, I just needed to essentially add this if block. So previously, we just evaluated the right-hand side of the assignment statement, get the address, and then store the value into that address. And now if we have an operation, we will also get the value from the left-hand side and call the appropriate function. So if we change our example here to say I plus equals 2, which is I is uninitialized, but let's not worry about that. And if we run it, so we will push d2, this is the r value. We will load the current value of I. We need to swap the arguments around. Then we call add. We duplicate the value, so because this is also the result of the expression. Store that in a variable, and then remove the value because we're having an expression statement. So like the value that we're moving would be like we can print it like so. And like this prints too. So this is the value of the expression that we are popping here. Okay, so that's assignment. And before we do anything further, we are now having debug occasions available. This means that, for example, when we use an assertion, something that isn't true, let's say I equals 10, we get panic from our local library, because the assertion failed, and it will print a backtrace. And this label here refers to the instruction that failed, so this assertion. But this is not useful unless you also print out the bytecode. So let's change it so the backtrace prints out the actual source location of the function instead. And this is done by default as if we tell Lauf where the instructions come from. So what we need to do is generate debug info when generating code. So to do that, we need to adjust, like essentially every time we generate code for an expression, we need to tell Lauf where the instructions came from. And I think one very easy fix would be to say that do it on a per statement level for now. So we only associate debug info per statement. And all we need to do for that is when we get, for example, an expression statement. So this means before we start generating expression any statement, we want to generate debug info. So let's actually write a little helper function generate statement that just takes any statements node and then we want to generate debug info. So let's query the location from the AST, context AST. Oh, it's not called context, it's CTX. CTX AST location of this statement node. This location is just the range in the input. And so what we need to do is convert that into the actual line location, which is a bit annoying. Because we need to know the input. So essentially we need to walk over the entire ST, entire file to compute the line and column information. So let's remember the input. Compiler. So this is the input. We need to store that in our ST. Which means that we need to include Lexi stuff here, Lexi input buffer, and then CodeGen compiler needs to store the file. Okay, this works. Now we just need to set that in the compiler. So when we generate the AST, we also want to state AST. We're not storing it yet, so now we can store the input. Let's just do a reference to the input and assume that this holds long enough. State input. Input isn't the nicest code, but it's C++, so that works. So now we're setting the input, which means that in CodeGen, we can get the input from our context and convert that into, let's call it expanded location using Lexi get input location of the context AST input of the buffer. We want the begin and we don't have an anchor. And then we need to include the relevant header, Lexi input location. So now we've converted the pointer into line and column number, which we can then create debug info. Love Adam debug build debug location in our builder, which sets the debug location for everything that comes until the next until we change it. So this is then the expanded location dot line number, expanded location, column number, and false. And then this is UN 16s. What happens when we do that? Okay, we're not using it. And then we want to generate the actual code for the statement. So we visit so I want to do that before we visit every statement. Let's just invite the client and worry about it later. So generate debug location, and then we want so ev statement if ev. So if we're entering the node for the very first time, enter, then we want to generate debug location. Else we do the actual code. So traverse event ev, right, traverse event enter, generate debug location for the statement. Else we do the actual code. And now we get an assertion failure because it doesn't like the pointer. What is the pointer? Yeah, that pointer doesn't look correct at all. Oh, what is context as location of statement? Is that maybe null? Let's assert. Every node should have a location. Nope. You know what? Let me do this. So let's enable the sanitizers and see what they say. It's probably because we're storing a pointer to the file and that file has since been destroyed. I'm thinking that's the issue. Yeah, stack use after scope. So we are creating, so we're storing a pointer to a temporary. Remember like 10 minutes ago and I said we shouldn't store a pointer, that's probably not a great idea. Exactly what went wrong here. Can I copy a buffer? I can copy a buffer. Okay, let's do a copy then. And like, if we were programming in Rust, the borrow checker would have caught that error, because it would have detected that we're storing like a dangling thing at this point. But like, it was literally like a 1-minute fix, right? Just enable sanitizers. They tell us it's a stack use after 3. The core stack would have told us exactly what went wrong here, so not really an issue. But we're still getting the assertion failure. So maybe I should have. I spoke too soon. I'm now copying the buffer. What's going on here? Okay, maybe Rust would have helped. Let's get input as with input as buffer. Oh, right. Okay, so now we are copying the file, which is of course wrong because the pointers point to the out file and that is still destroyed. So this again would be an issue that Rust would have solved for us. I'm very surprised that the sanitizer isn't complaining about it. So that's weird. Let's do, let's do the following. Let's move the file. So when we copy the file, here we are copying the memory, but the local position pointers point to the old memory and not the new one. So let's move everything over. And now we're getting a memory leak, but that's fine. Right, so now we're getting like line and column information for every individual statement. We are still now just need to tell it the file now that those are coming from. So so when we create the context, we also say love set module debug path of the module is asked input path. And now we still have the memory leak. It tells us exactly the location where the stack trace failed. Test.c 55, which is exactly here. So the beginning of the statement. So that's good. One last thing we're doing, like those statements here at the end, they essentially do return 0 and also free the local variables. Those are not at location 5, right? This would be, they are like synthesized. So let's adjust that in the codegen. So which means at the very end, when we generate the implicit return 0, we also want to specify a different debug location, 0, 0 synthesized. And now, yeah, all right, we are saying those are at synthesized location. I need to fix them so we don't actually want to print the debug location. And it says that this is like a synthesized location. It doesn't map to the program. But those are very simple debug locations. I believe it. I think it's totally fine if you do it on like per statement basis. If we could extra fancy, we could say it like, for example, test.c. Like we could say that this push 11 has this offset. Right, it's here, and this store local values, then this assignment operator, but this sort of fine-grained information isn't really necessary. I just wanted to get nicer stack traces. Because especially when we do now a bug in, like, let's say here, and this is 2. So if we do have bug in our tests, we will get a nice stack trace that has exactly which assertion failed. So that's great. We already have nicer features than C. Okay, so let's commit that. Generate debug information in love bytecode. Okay, let's add actual features to the compiler now. So what I want to do today is build global variables. And then we do calls, and then we move on from there. So the first thing we need to do for that is we can currently do something like this. And now we're having 2 main functions, which of course isn't ideal. So let's fix those. So we need to detect when we have declaring the same function multiple times. And what we are already doing that for local variables. So we're having a simple table. Let me go to the code. Variable declaration statement. Here we go. So we iterate over all declarations that we're passing and insert them into the simple table. And if they shadow an existing one, we generate an error message that we're having a duplicate declaration. And we can do the exact same thing for global variables. We just need a separate symbol table for those, because the symbol table for local variables is cleared whenever we enter a function, because like you can't shadow between function scopes. C of decl. So these are the global symbols. Okay, so global symbols. They're initially empty, and whenever we visit a declaration, we want to add them. Well, we don't know. Not whenever we visit a declaration. Yeah, because this is done in part of a declaration statement, then we pass a declaration, which isn't at global scope, it's added in the local scope, so this is fine. So the only thing that's currently at global scope is a function definition. So we want to add a function definition to the symbol table. So this is our new function decl. We're creating it here. And then we want to add them, essentially copy the exact same code over here, just for a different symbol table. So state global symbols. Name of the function decl, the function decl. So duplicate global declaration like so. And now when we run it, right, we want to return the declaration. We're getting an error message that we're having a duplicate global declaration of the function main. I don't like this code duplication, so let's write the simple function. my editor hanged, like so. Insert new decl. So into a symbol table. Decl const jar scope name, and then we also need the state to be able to generate the error message. And then we decl statement. We do that. So we insert that not into the local symbols, but into the symbol table. Duplicate scope name like so. We need namespace, and instead of taking the entire state, let's just take the logger, because that's all we need. We actually not, we need the entire state. Okay, let's just take the entire state. And then decl statement. So now we go ahead and do insert new decl, state, local symbols, decl, local. Now give that function definition. State, global symbols, decl, global. Okay, that works fine. So let's commit. Okay, global variables. Let's see what happens when we would try just write one. And see what happens. So we got our function main and I. We got an error, and then we got less than ideal behavior because we are returning null somewhere. So the issue is that's a peculiar, right. So what happens here is that we are trying to pass a function declar, a function definition, because we've defined the translation unit to be a list of function definitions. And when we pass a function definition, we pass a type specifier, a declarator, and then a block statement. Right, at this point, we don't complain that this doesn't look like a function, this looks like a variable. It will just attempt to pass a block statement and then complains that it doesn't contain a block statement. And then it produces a null pointer somewhere, and we have to handle those sort of errors more gracefully, but that's an issue for another day. So that's the issue. So what we actually need to do is look at the grammar. So a translation unit consists of an external declaration, like a list of external declaration, which is either a function definition or a declaration. So what we actually need to do is either we pass a function definition or we need to pass a declaration. The issue is that like the beginning of a declaration and a function definition looks identical, right? Only when we see the semicolon do we know, this isn't actually a function definition. And the way parsing in Lexi works is it doesn't do implicit backtracking. You have to tell it up front whether or not, like which approach, whether it should be a function definition or declaration. And this sort of is a bit tricky because like we need to do a lot of look ahead to get to that point. So instead, what we're going to do is we're going to pass the rule entirely manually. Entirely manually, like pass the beginning of a declaration and then see, do we have something like a block statement, in which case then we turn that into function definition. Otherwise, we execute the code for declaration. So let's write a new grammar rule. Let's just call it, they're calling it external declaration. I don't like this name because this can also be a static variable, a static global variable would also be an external declaration, but it is not external. So let's just call it global declaration. And we are being a bit loose in our program with declaration versus definition. Like we're calling everything a declaration, even if it's a definition. But that's okay, I guess. So we want to pass a global declaration. We want to pass it manually. So this is a scan production. And then we get something like, I always forget. Let me look at the Lexi documentation. Right, I can't actually move a window over while OBS is running. This is like a privacy protection thing, so it has to stay on the other monitor. Sorry about that. So scan production. This looks like, okay, so this is what we want. And then you also, this isn't like, we need to specify the return type here, which is a pointer to the declaration. Okay, and now we get a scanner and we can manually pass it however we want. So we want to pass like the beginning of a declaration, which is, I guess, like a declarator. Like we want to pass type specifiers and then declarators. So specifiers, let's go specifier scanner.pass grammar type specifier, not specifier, return scan result. Scan, what's it called? Lexi scan fade. Okay. Then we want to pass the declarator. If that failed, then we fail. Okay. Now at this point, we might at this point look whether we have, because if we do, we're actually passing a function definition. So scanner.peak. So if the next character would be that, then we're passing a function definition. Otherwise, we want to pass a semicolon. Wearing a declaration that isn't a function definition. Okay. So if we have a function definition, then we want to pass, first of all, we want to, how do we get the pass states? I believe it's passed as a separate parameter, so the compiler state will be passed here as well. So we want to start passing a new function, so we need to clear all the local symbols. Yeah, local symbols here. And then we want to pass the body. Scanner.pass grammar, which is a block statement. And then we can do all of that logic. So this is called decl, and this is called type. Let's just non-function definition. So that's that. And now a translation unit is a list of global declarations. Now matching function to no try-cars. Alright, because this is decl value, type.value, body.value. invalid argument type. Alright, it's scanner.pass, not scanner. Binding dereference null pointers only for behavior. Okay, man, unreachable isn't that. They don't like that. So let's return that. Yeah, so that actually triggers the to-do. Do the tests still pass? The tests still pass. Excellent. So what we did is using like the ability of Lexi to do manual parsing of any production. This is now pretty easy because we can just pass the things and then make the decision. With pure Lexi code, this would be a lot difficult. The downside is that we need to do a lot of boilerplate, like all this checks for whether the scanner failed, like what we previously did, where we could just chain the individual productions. That was a lot more concise. Okay, so now we just need to create a local definition, I guess. And this looks like essentially we invoking this callback, which will get us. We actually have a declarator list. That is interesting. Let's worry about that later. So what we can now do is we pass so the grammar declaration. We just invoke the callback. And we pass it the state, the type, and a list of declarators. So the state, the type, declarator list dot push font decal dot value list. Oh. Really? Everything else is const expert? Okay. Right. We need to invoke that using this syntax. And now what we get is we get a list of declarations, right? So let's turn this one instead of like, because we can declare multiple things with commas in one declaration, this also needs to be a decal list. And then here we're creating a decal list. My language server is dead, so list pushback function decal list decal list. Missing sync value callback overload for production. For which one? Translation unit? Oh, right. The translation unit actually returns a list directly. So that's nice. Oh, wait. This is a list of list. I've got like concat. Concat. All right. This is. Let me just hack that and fix that later. The upside of implementing every other library you're using is that you can easily fix issues. The downside is that there are probably more issues than if you didn't have them in the first place. Incompatible pointer types assigning. Okay, let's look into that. Worry about that later. So let's just get a vector of decal lists, and then callback compiler state a vector of decal lists list. We manually merge them into a single one. Decal list decals for auto. List of list. So for each list, for each decal in list, decals pushback decl, and then state as create a translation unit. We also getting the location here. Block decls as include vector. So the issue here is that each global declaration is actually a list of multiple declarations, and then we're having a list of those, and we need to essentially flatten the list. We're having the exact same issue, funnily enough. Assigning to seal of decl from triad node. What exactly are you complaining about here? Let me get my language server back. So the constructor for translation unit takes a list of declarations, but we're creating a list of declarations. So what exactly is going on here? So we're iterating. Oh, it's a bug in this library. I need a downcast here. Okay. So all that code was essentially unnecessary because we could just do that. So 2 bugs in 2 libraries I need to fix in order to get that to working. So this now works. We're still having the memory leaks. And it only works insofar that, I mean, it actually works properly. So what do we have here? It takes some time. The sanitary code always takes a while to compile. So now we're having a translation unit that consists of a function decl, a function type, and a block statement. But where did the global variable go? We're creating it, right? Yeah, I mean, like, we're creating it, and then we're doing something with it, I'm assuming. Maybe it's just not printed. No, I mean, it should be printed. Let's see. Let's look in the constructor. Let's begin. So the first one is it's a function decl, but it shouldn't be a function decl. It should be a global decl. And so, okay, so we're only creating one. So where did the other one go? What if we don't have a main function at all? What happens then? Program does not contain main, but now it contains the... Okay, I think the concat implementation is actually broken. So, we should be here. So this is an ast symbol whose kind. All right, now we're getting it anyway. Oh, right. Okay, so we are trying to add an element of type variable declar into an empty list. Okay. What the hell is going on here? This really doesn't like. Let's just do the thing with the vector. There is some bug there I don't want to fix. Spent ages debugging it. So we again do the vector thing. Then we have a callback that returns its translation unit. Which gets the compiler state, which gets the vector declar list. We lower that to a real one. And then we create the node. And then we get the includer again. Okay. Right. The issue here is that we're returning pointer. Okay, now we're getting both of those. There's a bug somewhere in Concat. Okay, we are now getting the AST that contains global variables, but we also need to add them to the bytecode. So let's add them to the bytecode. This is just the case of when we visit a node that is variable declar, we just need to generate a new global, add global 0 data, so 0 initialized global variable into our module, and since all the type are ints, we are having this layout. And then we also need a map of all the global variables. So of variable decals to globals. So in the context, globals dot insert the node, and this is the global, and I actually don't need to specify a pointer right here. Okay, so now we are should be generating code for global variables. Right. Oh, and we are having const. Okay, so now we are generating the global. We are losing name information, but that's fine. So we're creating a global variable of type int, and ints are 64 bits, so we're reserving 8 bytes. Okay, so that's globals. And of course, we can assign globals, and this is going to fail. Right. It's first going to fail in the AST. In the compiler, because we're not doing lookup in the global scape. So let me restart so I get my language server back. Identifier expression. So if decl is null pointer after looking in the global scope, then we look in the local scope. After the local scope, we look in the global scope. This matches the semantics where a name in a local scope can shadow the global name. So we have to always look in the local one first. So now, alright, it would have helped if we also insert them all into the global schema table. So let's do that. Insert in the decl state with global symbols, decl global. Okay, and now we're getting an assertion failure in CodeGen, because we can now have an identifier expression that can refer to a global variable, but we haven't taught CodeGen that. So it looks up, right, this assertion fails, because we're looking up in the local variable, but this can fail. So then we also look in the global variable. All right, context globals. Look up. Okay, so if was null pointer, after then we check whether this is if this is a var decl. So try it now, try cast clog variable decl expression declaration, and then we look up the var decl. Okay, so let's do it this way. So if we have a local variable, let's do it that way. Okay, so if we're having something that actually is a variable, then if it is a local variable, we do that. So decl, and then we push local var onto the stack. Okay. Otherwise, if it's a global var, context globals look up our variable decl, then we push value local var, push the value of global var onto the stack. So this looks the same. Instead, here we're having global address, and here we're having global var. Then we're done, and then we're done, and here we're doing an unreachable. Currently, nothing else supported. Right, because an identifier cannot refer to a function and so on, but we don't have those. Right, so this is actually, this still fails because we are only handling code that gets the value, so we can print a global variable now. That is the code we just changed. Right, we can print it, has been initialized to 0. Great. So what we need to, the code that we previously had was assignment, and this is the code for assignment here, where we're getting the address. So we need to essentially copy the exact same code which means it makes sense to extract them into a function. So auto get, I'll do that off camera, figure out the correct abstraction. Let me just copy that. And we just want the address and sync up unreachable. We don't support anything else yet. And this is called expression. So I equals 42. We've got our memory leak, but apart from that, we can now print 42. So we've got global variables, we can create them, we can read them, and we can assign them, which is great. Global variables. Now there's one syntax thing we need to we should fix up before we move on, because we can also have this syntax, and this shouldn't work yet. Right, because when we pass a global declaration, we're assuming that we have a semicolon, when instead we could have more declarators. So let's actually pass a declarator list. Yeah, this is a production that we have. Declarator list, decl list, decl list. Because in a function definition we don't actually have a list. So decl list dot value dot front. I don't think I have front. Let's just do a celof assert decl list. Let's just crash and worry about that later. Actually, we don't crash because the declarator list by definition passes one or more. It's a list, not an opt list, so we always have at least one. But we need an issue if we have more. We need to issue an error if we have more than one. To do generate error if more than one declarator in function definition, because that's not actually allowed. And so here we want to create a decl list. Right, of its value. Right. That thing again, because the issue is that we are having, this is, wait, where is the assertion coming from? Oh, because it's already part of a list. I need to, interesting. Let's, you know what, let's just leave this bug in. I'll fix this off camera. So the issue here is that we need a way to transfer nodes from one list to another. It's intrinsically linked list and they're already occupied, so we can't push back them because it's like assumes that this is not yet part of any list, but it is. We need to properly transfer them, which requires API changes there. So I'll do that off camera, and we just do a partial commit here. Pass the correct syntax. Okay. We have an assertion failure when merging the lists. Okay, I'll fix that off camera. So now we've got global variables. I want to get to function calls. We spent a lot of time on the concat bug, so I don't know how fast we can get there. But before we can actually call function, let's add return. So return statements. So we can have something return statements. Since all we're having is void, We don't have a void type yet. We are only supporting the version like return value, not the return semicolon one you can use in the void function. Return statement. E.g. return 0. So return statement, return statement, return statement. It just like an expression statement, it has an expression as its child, which is the expression that we're returning. We need to update the est dump for return statements. So this is a return statement. We don't need to print anything special for it, so let's move straight onto the parser. We can copy essentially what we did for expression statement, but just say that we start with a return keyword, then we're having an expression, and this will use a return statement, and this is called return statement, and a general statement can also be a return statement. And we need a new keyword. Return. Which means that we need to reserve the identifier return. Okay. Now we can parse return statements. Okay, so right here we can pass return statements. We need to add them to CodeGen. So we are visiting all the statements somewhere here. Right here. So when we have a return statement, we want to generate debug info. So the underlying expression has been visited, and we return. So we return in the builder, and this will now also terminate the current basic block. So in Love, everything is organized around basic blocks, and return statement terminates one, so we need to start a new one. Next block. Declare block, which takes no arguments. This block isn't actually reachable, so let's call it unreachable block, because after a return statement, like, we're done. But if we have statements, we essentially need to have one. I'll show you an example. So start building in this block. So the unreachable block. So what's happening here is here we are returning the value of our global variable and then create a return. And then we continue on, and at the very end, add an implicit return 0. And this needs to be part of some basic block. Otherwise, we will get an assertion failure in Love, because every instruction needs to be part of a basic block. So after the return statement, we start a new basic block. This code is not reachable because we're returning and never jump to it. But like, we could also check whether we currently have a block. But it's easier if we just generate a basic block, add the instruction to it. They will never be used, but that doesn't matter. So now we got return, which means that let me actually disable the synthesizer so we get the correct return type. So now we exit with execute 42 because that's the value we assigned our global variable. So we've successfully implemented return statements. Okay, next up, function calls. So this is a primary, no, this is not a primary expression, this is a postfix operator, function calls. So the grammar is we're having an expression. Essentially, we're having like we have an expression, and then we have two bases. We don't have arguments because we don't have parameters. So simply an expression, then two bases, two parents, and this is a function call. So we need to add a new kind of expression, a function call. Let's add it here, function call expression. And now how do I want to do that? So a function consists of two things. It has, let's do it properly. So function expression. This is essentially like a unit expression because the thing that we're calling is another expression. It can be a name, but it can also be like a dereferenced function pointer or something like that. So this is another expression. So a function call expression also has a child expression, which is the function that is called, and then it would have the parameters. But we don't have them at the moment. So this is the function that we're calling. And then we don't have any parameters. We don't have this one, we don't have this one. And the type is called function. Function. Why am I getting a bunch of errors? Oh, I forgot to add it. Oh, right, it's called function call expression. Function call expression. Function call expression. And function call expression. So, then the usual thing, we need to add them here. Function call expression, function call expression. Okay, we're compiling. Let's add them to our parser. So when we pass an expression, we are having the grammar specifies like primary expression, this is our atom, and then we've got postfix expressions. And we're only having one at the moment. So postfix, these are a bunch of postfix operators. We don't have associativity for them, that's fine. So the operator in this case, the only operator that we're having is open base, open parent followed by close parent. Right, so this can be considered the function call operator. And then we would pass arguments in there. This 0 is here because you can specify an enum value. I don't have an enum, so we need some value there. So that's not important. And the operand is the atom. And the operand of a unit expression is now a postfix expression. This means that we need a new overload right here. So when we're getting called with an int and a child, that is a function call. And again, we're hard coding the type because we're only having one type at the moment. So this is a function call and that's it. And this object, it also stores the location. So we still need it, right? Okay, so now we're creating a new node for the function call, which means that if we fix the remaining errors, all right, this is a postfix expression, so the operator comes after the child expression. And the child expression in this case is the function that we're calling. Okay, this compiles. Let's actually implement a function call, and let's just do infinite recursion for now. So this is something that we can now pass. Except we can't, because the name isn't that's a nice, well, it's not nice, but it is what it is. So the issue here is that when we pass a function definition, when we pass a function definition, hang on, the live stream disappeared for me. Okay, now I have it back. I don't know whether that actually disappeared. Anyways, the screen just went black there for a second. So the issue that we're having is we are adding the new decl only here. But at this point, we already passed the body and attempted to do name lookup. So what we actually need to do is generate the new nodes first, then pass the body, and then set the body. So this means that we initially don't set the block. Instead, we have void set body, which takes a statement list body. We assert that body dot empty. So this should be null pointer. Okay, so then we set the body. What was the... of course, we need a pointer. Okay. And then when we do we can do all of this first. Then pass the body right here. Set body value, and if we don't have one, we fail. Okay, and now it has we're getting an assertion failure in some downcast. Oh, right, because this is no pointer. Let's just ignore that. Okay. So we are passing it. Right, we are properly passing a function called expression for a function called main. And now we're reaching an unreachable code in CodeGen because this is 191 right here, where we're having an identifier expression that is not actually a variable, but a function. So if we're having a function decl, then what we want to do is add the correct amount of parents. Then we want to push the address of the function onto the stack. Right. So for that, we need to figure out which function it is, and for that we need another kind of simple table. So for function decls to functions. So this just means context functions dot lookup function decl. We don't have function definitions in the inner scope, so this isn't an issue. We can just assert that we've got one here. We don't need to look in any other table. So this should not be null pointer. Forgot to populate table. And then we want the address of the function. Okay. So this now pushes the address. We of course also need to populate the table. So before we actually start, yeah, let's do it here. So context functions dot insert the decl. Oh, right. We have to do it here. So here we create the function and then we do context functions dot insert decl fn. And this modifies the context, so we need to be able to modify the context. And then we need to return here, so we don't trigger the unreachable code. Okay, but we're still doing nothing because we are ignoring function call expressions. They currently generate no code and instead just fall to the identifier expression. So we are pushing the address of the function and then popping it, which gets constant folded away. So we need to do something for a call expression, which looks like so. Call expression. At this point, the address of the function has been pushed onto the stack. Call it since we don't have any arguments to push. So, and we're doing an indirect call via the address. And the signature of currently all functions, they take no arguments and return one value. And now we're getting a very long stack trace because we are essentially having a stack overflow, right? Because we are having main that just calls itself recursively forever and ever, right? So let's actually lower the stack trace a bit by pushing a bit more data on it. Let's see what that does. So now we are printing. Now we're having an infinite loop of some sort instead of a stack overflow. That's very interesting. But okay. I don't know why we're now not getting a stack overflow anymore, but that's not important. Let's do something like so I equals 0, then we evaluate 0. Otherwise, we do I minus 1, like so. And this does nothing because I starts out at 0. So let's call this one f, and then main sets I to 10. We're calling f, and let's just say print I. And now we're counting from 10 downwards. That I'm actually surprised that it just worked out of the box. So we've got basic function calls. We don't have any parameters, so we need to communicate state via global variables. But this is something that we will fix soon, obviously, anyway, right? So that's great. The function call, right. This is a very complex expression, right? It reads a global, compares a global, modifies a global, calls a function. It would be great if we had if statements, so we wouldn't need to use like the ternary operator, but that's fine. Let's commit, and then see, implement function calls. Let's write a real program to test how fast the compiler is. Or rather the interpreter. So let's write one that computes the Fibonacci numbers recursively. So we want to return n less than or equal to 2. If n is less than 2, then we just return n. Otherwise, we set let's prepare variables int n minus 1, int n minus 2. N minus 1 equal to n minus 1, n minus 2 is n minus 2, and then we set n to n minus 1, call flip, plus n equals n minus 2 for a feed. Multiple unsequenced operation to. Right, this is undefined behavior because we're modifying the same variable within one expression. But this should work out fine because we're writing the compiler, and I believe the evaluation order that we're doing matches what we want. Parameters would help there, and let's just say print big for the 0, 1, 2, 3, fourth one. So the idea of Fibonacci is 0, then we've got 1, 1, 2, 3. So this appears to be working. Right, then we've got 5. So let's do a bigger value. So computing Fibonacci numbers is recursively takes exponential time. And I shouldn't have executed it in debug mode, because this is going to take ages. Oh, we actually got the value in 12 seconds. So that's great. Let's run it in release mode and see how fast it is. Then so it takes a while to compile, especially Lexi. Translation units that use Lexi aren't easy for the compiler to compile. And 1.6 seconds to compute the like the 35th Fibonacci number. Let's just for fun. So if we remove, instead do a return here. Now this is code that Clang compiles. I wonder whether Clang uses the same evaluation order. Let's just hope it does, so we get a fair comparison. Return to right. We don't actually. Let's just quickly print the value out so we can see what value we're getting. Right, we are writing C code. We're writing C code. So we're getting the same. Clang happened to pick the same undefined behavior interpretation, so we can do a fair benchmark. Command didn't execute it. Okay, let's do that. Let's see how long it takes. So it takes about 1.76 seconds. And Clang, including the compilation process, is about 8.2 points faster, which isn't ideal. I mean, it is an interpreter, so it's always slower, and this is like a really stressful benchmark, because like it really is really inefficient code. But let's see where exactly the performance is coming from. So let's see which function are important. So we're doing a lot of integer comparison in our VM, which makes sense because we need to do much of comparison. And then we are having this one, 11% is dereference. And this, the issue here is that we are generating bytecode. We don't have parameters, so we use global variables. And if we take a look at the bytecode that we're generating, this has a bunch of, we're taking the address, then we are dereferencing it, and then we're loading its value. And low is a fully sandboxed VM. which means that it can detect whether or not you have an invalid pointer. But this adds overhead, right? This isn't just a simple let's modify it by pointer, right? The actual assembly code that Clang generates also does pointer arithmetic to access the global variable, but it's a lot cheaper because it doesn't have this extra sandboxing step to determine whether the pointer is valid. And this is where a lot of the overhead is coming from. So if we implement parameters, then I believe we will get a performance that is a lot faster. Because we eliminate a lot of this address calculation and instead only dealing with values that we can. Because there is an optimization, right? When we access a local variable, it knows that statically the address of a local variable is fine. It's valid, so it doesn't need to do this extra indirect step where we first dereferencing it, which needs to ask is this a valid pointer, and then call the user-defined function to load the value out of that address. It can just hard-code it, do it at the local. So this is a lot faster. So when we have parameters, which are also locals in that sense, this should be a lot faster. But that is all I wanted to do for today. So we implemented global variables, return statement, and function calls. And there was a bit of a struggle with some bugs in the libraries that I'm using. I have to fix them off grammars and do some nicer things, but this is still, I believe, it's pretty nice. So next time, just actually let me see what happens. Maybe it just happens to work. If we do, it doesn't, it won't work, right? So this is something that we also need to support, right? Because yeah, so. It's still, but the basic support is there. Thanks all for stopping by. I hope you enjoyed the stream and have a great day. Bye.